things. Not a single thing I say on this slide will be a surprise. How come I don't have response here? Hello? There we go. All right, so the places where we're going to test, we already talked about yesterday, the critical points. We understand what we mean by that now, right? Places where the derivative is 0 or undefined are the places we care about. And then the next thing we want to ask, and this goes to answering Rosa's question, in one slide, you'll know here, we want to know what happens to the sign of f prime. And like I said, I already know that you thought about this because, for instance, when we were doing velocity and acceleration and all that stuff, position, we asked you that question. Did the particle, at what points did the particle like turn around? Didn't we ask you that kind of question? And you understand that the velocity, for example, had to go from positive to negative, or from negative to positive in order for that to represent a place where it changed direction. Well, that's exactly the same situation here. So if f prime changes from being positive to negative, then what happened on the graph of f? It went from doing what? If f prime is positive, that means the original graph was increasing. And then after that, it was decreasing because f prime was negative. So what was that? Well, I think if we just go visual on this, it's pretty clear to me that if we did that, then the point we're talking about is a maximum. So that would be my way to check that maybe. But again, I'm going to use like a number line. I'm going to test some points. So again, that picture could look either one of these two ways, couldn't it? Right? Could be a place where f prime is 0 or where f prime is undefined. Okay? Of course, we could say the same thing about negative to positive, being a minimum. So nothing to say there really. Could be a cusp or a corner. Picture maybe says it all. By the way, these are just ripped out. All this stuff is just ripped right from your book, so there's nothing. Or this is public domain information. You can find this all on the internet too. So I don't have I should have copied that one. Am I right that there's no surprises there? Okay. And then of course, if f prime, the last point there, if f prime doesn't change sign, then it doesn't have an extreme value there. So I think you'll be glad to hear that because that kind of like finally puts the finish on what we talked about yesterday a little bit in the way that like I think you, Rosa, will appreciate, but others too who might have had like questions about that, right? So when it actually comes to a function, and we'll do this here in a minute, this requires us actually plugging in a point on the left and on the right of a given critical point and seeing whether the derivative there is positive or negative. I'll let you stare at that. By the way, this is called the first derivative test, if that's not clear. This is what we mean by that. It's whatever critical point we currently have under question.
Okay, so C stands for critical point.
Yeah, I mean it's a constant, okay. So it could maybe stand for constant too, but it's where x equals some value under consideration. It could stand for consideration.
Okay, so it's just another number, right?
Yeah, it's like it's a particular value of x that we're interested in talking about right now.
Oh, okay, so
right. Notice we've used C before, like in the mean value theorem, we said like there exists a C such that the following is true. Yeah, I think it might have been the same C didn't we use C in the intermediate value theorem too, maybe? I don't know. whatever, it's just kind of tradition. It doesn't matter, it's just a stand-in letter. And then the third picture is here. I don't know that you need it, but right, obviously it's possible that the derivative is 0 where there's no extreme, or it could be that the derivative is undefined and there's no extreme value. So, pictures, again, pictures kind of are the whole way in on this. The only other piece we have to maybe say, and again, I only am going, this is hard to read, but it's very easy to look at, right? At left and right endpoints, we have to like say something else too, right? Because there isn't a notion of f prime changing from one sign to another. So we need to talk about what it means for an endpoint to be a maximum or a minimum too. So this should make, again, the pictures make this very clear. If f prime is less than 0, that means it's decreasing. If we're decreasing away from a left endpoint, that means that must have been a maximum. Or if we're increasing away from a left endpoint, then that means it must have been a minimum, that endpoint. And, so those 4 things are the other little endpoint cases that could happen. Again, no real huge surprises for you here. I don't know. Right. Yeah, exactly. Yeah, we still have no notion of the whole picture and what would be a bigger, because there might be multiple critical points, but all these tests are for local extreme values, right? Yeah, absolutely. In fact, the only way to test for absolute maxes and mins would be to actually evaluate the function at all the different places and test them like you did last night. So yeah, that's a great point to make. Again, this is a local, all these words here, local, local, local. Everywhere. Are you okay with A and B, Albert?
Yeah.
Okay. A on the left, B on the right, C in the middle. You can name it whatever you like. Okay, you still good to get on this? Do you anything else? You good? Okay. You let me know. Wave wildly if you need it in a second. Do you actually? The next discussion is about concavity. We want to talk about what it means for a graph to be concave up or concave down. You already have a sense, I think, of the fact that like these two pictures are different. What's the difference between like I don't know, an exponential growth curve and a logarithmic, an increasing logarithmic graph? Those were like completely different functions, and yet the language of the first derivative doesn't actually help us very much. In both cases, all we have is like, all we can say is they're both increasing. Well, that's not super informative when we know they're like very different functions. So we need to describe the difference somehow else besides saying the word increasing. Well, we would call this one concave up and this one concave down. And this says what that means here, right? And I have a picture to go with this too. So this is, you'll like this. This is us like surfing the function. What happens, and I think we've thought about this before too, in the context of position, velocity, and acceleration is when we were thinking about this, isn't it? Right? It's like now we're asking, what's the change in slopes like as we go from left to right? Now I'm likely to compute f prime for various values and ask, is f prime itself going up or down? And here I think you can see, isn't it, if you were like, even with my simple picture up here, if you were to draw tangent lines here, they're practically 0 in slope, and then, you know, 1/2, and then 2, 1, and then 2, and then 3, and then 4, and then 5, and then 6, they're getting steeper. The actual slope calculations as we go from left to right are increasing. F prime is increasing. So concave up, right? Does that make sense? Like if you're surfing it, your surfboard is turning counterclockwise. Yeah? If you're actually, your hand is turning up if you're like tracing the graph with your hand. Over here, it's hard for someone to look at this and be like, there is something decreasing about this graph. But there is something decreasing about this graph. The rate at which it increases is decreasing. Do you see it? I mean, you have calculus eyes now, so maybe you do see it, right? It is increasing always, true. But f prime, as we compute f prime values, as we go from left to right, that numerical slope value is actually going down, isn't it? Goes from like, you know, +7 to +6 to +5 to +4 to +3 to almost 0 here. I think even though those are all positive slopes, aka the graph is increasing, they are less so. The actual slope values are going down. That means it's concave down because y prime is decreasing on that interval. These arrows kind of say it again, yeah, right? So concave down, your hand, as you turn along this curve in this picture down here, your hand is turning clockwise, and then your hand starts to turn counterclockwise over here. So if y prime is increasing, then we can apply the thought process we had earlier. What does it mean if y prime is increasing? How do we know whether y prime is increasing or not? Well, yeah, we could ask whether y double prime is positive, right? So that's equivalent in every way to the thing we just said, right? Concave up if y double prime is positive. Concave down if y double prime is less than 0. So now we have like 3 ways of saying the same thing. F is concave up, y prime is increasing, or y double prime is positive. And say those things again for concave down, right? Does that make sense? 3 ways of expressing the same idea. And the place where the graph might change, you might think, what's the the second derivative analog to the first derivative discussion where like we had like a maximum or minimum? True. Okay, well what do we call that point where concavity changes? How about just a point of inflection? We don't have a better name for it. Whether the second derivative changes from positive to negative or negative to positive, we call that a point of inflection either way. Or POI for short. Now this definition I took from the book. This is actually hotly contested though. The thing we all care about is that I think we all would require a concavity change as you cross this point on the graph. It needs to go from y double prime being positive to negative or vice versa. But now this is weird here. They're trying to save us in the context of like the cube root function, right? Does it still have a tangent line there? It does. It's vertical, but it changes from concave up to concave down on the cube root graph, for instance. So they're like, so we don't insist that at that point of inflection necessarily it be differentiable. So they're using this language. I don't know that I would insist that though. I would just insist that maybe the original function be like defined there, maybe continuous at that point. That's not really going to come up in your life that much though. As long as you see a change in concavity, I think we can be safe about talking about a point of inflection. The next piece I want to throw at you too is, and this is a little bit of a departure from the things that all the stuff we've just been talking about comes right in behind each thing. You want to be like, oh yeah, this makes sense, this makes sense. This comes out of left field a little bit, but it definitely belongs here. Let's see if we can figure out why this makes sense. If on the original, this is the second, careful on the title here, this is the using the second derivative to make some determination about extrema. All the stuff up here, it seems like, hey, you know what the second derivative is good for? Up here, it seems like, oh, second derivative is good for concavity, and only thinking about concavity. But that's not necessarily the case. It might actually help us in the search for local extrema too. See if we can figure out why. If on my graph I have a point where I have a horizontal tangent line, that is if f prime is 0, And if f double prime is less than 0, what does this graph look like here? Now, I haven't actually drawn the graph. If f double prime is less than 0, then what does that say about its concavity at that point? Let me go back up here somewhere. Then it's concave down. So I haven't drawn the graph here, but if it has a horizontal tangent line and it's concave down, then how do I have to draw it? Am I right? Well, have I convinced you just from this picture that it must be a maximum? So do you see that, like sometimes, because these other pieces of the discussion earlier on, if you're testing for extrema, require that you test another value to the left and right, and sometimes that's like either like hard or like maybe it's just easy, it just happens to be easier, or you're lazy and you just want to check. Maybe it's super easy to test the second derivative at that point, and it's differentiable, twice differentiable. Then that's a great way to do it. So the same discussion here, it's just, right, you have this. For the second point. So that's cool. Let's call the second derivative test for local extrema. By the way, if you're trying to remember how to, I don't know that someone has to remind you necessarily, but if you're having trouble remembering that concave up means y double prime is greater than 0, you might think, okay, if it's positive, then it's up. Concave up, it has that shape, doesn't it? And if it's negative, then it's down, right? So it's like a sad face, like negative is sad and positive is happy. Like if the second derivative is, that's not really a stretch. Actually, it's a beautiful way to think about it. Come on, they're like happy and sad cyclopses, okay? We need to give them like, maybe they're aliens or something.
That's so disgusting. Alright, 5 arms.
They have antennas.
There's no eyes. There's 2 arms.
There's an antenna on top. All right. So, and actually, well, yeah, I'll do it up. I guess I'll. Yeah, maybe I'll do it up here. I don't actually have. I should have made a blank slide to work this out here, but it'll be okay. So I've done the hard work of factoring this for you already. I don't know that. I don't know. You might remember from pre-calc how you could get at this factorization using like testing some of the zeros and rational root theorem and all that. But I've done you the favor of giving you the factorization. There it is. But I don't know that you'll need it necessarily. Let's see. So let's actually find for this cubic. We already have a notion of how it looks, so maybe this is a good first one to do. Let's use the first and second derivatives to test for all the things we said we could test for. Let's see if we can find the intervals where it increases and decreases. Let's see if we can find places where there are maximums and minimums. Let's find places where it's concave up and down and its point of inflection. So I think we're going to need a first and a second derivative if you haven't done so already. So let's do that. Yeah. I might do it over here because that's something come up over here. All right, so here's my first derivative, and I'd like to factor it too. Why do I care about factoring it? Why do I care about factoring it? Are there any places where this derivative g prime is 0? There are, and I'm about to find them, right? Where they're what? X equals 0 and 2. Are there any places where it's undefined? No. I already knew that coming into the problem. This is like a cubic, polynomial, always continuous, differentiable. Okay, and then here's how this actually feels, right? You're going to put those two numbers on the number line in order, and we're going to ask what the derivative is in each of those intervals. I think we've just made a very, very thorough claim that the only chance that the derivative has for changing sign, that is from going from positive to negative or negative to positive, is at these places. So if we test over here to the left of 0, and we get that the derivative is positive, it is positive everywhere for every x value to the left of 0. even if, does that make sense? Because if you think it's positive, then we'll hold up. Maybe it changes somewhere over from positive to negative. Well, then that was our failure to find a critical point. Like, that's why it's important, hopefully, that we've listed them all here. So we've been very thorough. Hopefully, those are the only places that it has a chance to change sign so that we can engage in this discussion. So let's give an example of something less than 0. Like, how about -1, for example? If you plug that into the derivative, what do you get? And remember that I don't actually care. I just care about whether it's negative or positive. It's a negative times a negative, so it'll be positive, right? In between here, if you plug in 1, you'll get something negative. And then if you plug something really big in, like 3 or 3,000, you get something positive again. So this was my story about G prime. Can you now tell the story about G underneath? What happened to G? If G prime is positive, G was doing what on that interval? From negative infinity all the way up to 0. It was increasing, and then decreasing, and then increasing. So what's that? X equals 0 is? No. It was increasing, visualize with me.
It's a maximum.
And then decreasing. So that was a max. And then here, decreasing, then increasing. Like I said, on this particular first example, we're using a cubic. I think you already know what it looks like, don't you? So hopefully this all just confirms your intuition from recalculus. We'll do more exotic functions soon that like you won't maybe have as much intuition for, and you'll have to trust the calculus a little more. But here, definitely, this is confirming what I think I already know. Great. What's G double prime? So we need to write it up nicely, right? But we've done what we need to with the first derivative, and discussing increasing, decreasing, maxing, min. All right, second derivative is what? 6x minus 6. So when is that either 0 or undefined? Only at x equals 1, right? So let's do the same thing with G double prime. Not a very interesting number line, but there it is. When is the second derivative positive, and when is it negative? Well, yeah, over here, I think if we plug in a number like 0, we get something negative. And over here, if we plug in a number like 2 or 2,000, you get something positive. So what does that say? G double prime, we just said G double prime, is what we just said, is going from negative to positive. So what's happening again with G? Let's tell the story about G down below. That means G was doing what on the interval from negative infinity to 1? What kind of behavior does it have? Yeah, concave down, we'll write CCV just for short. And then G is over here, concave up, and this must be then, since there's a change in concavity, we got 3-letter acronyms for all, or start abbreviations at least. Okay. There we did. Now we've done it. Now the thing is, this is not sufficient. If you're, this is good. If you're going to write this up, now I want to keep in mind that we often, we or AP will ask for only like one of these. This is a pretty exhaustive list of things we've just done. They'll ask you a lot of times to justify, to find the intervals of increasing. They might just say one of these things. Give the intervals of increasing and justify why those intervals are increasing. If that's the question prompt, then it's not sufficient to just show this work. They actually want you to write words. So after showing some adequate maybe working math, then they actually want you to list out this kind of stuff for each of these. No, listen. Like I said, Albert, listen and stay with me here, okay? Like I said, normally you would only be expected to like write one of these sentences. They're not going to ask you to to ask this. Find all the intervals of increasing and decreasing, points of inflection, maxes and mins, and concavity like intervals and all that, and justify them all. Go. I'll see you in 20 minutes. They're not going to say that. They're going to say like, justify why like f is concave down on the interval 1 to infinity or something, or negative infinity to 1 or something. So, but this is, I want you to stare at my language here because I've worked hard here to write what we think that AP would expect of you, right? Why is it? It's not just because of like some number lines that maybe you like don't actually understand. They actually want you to articulate with the words. Do you actually understand what you did, or are you just like a robot doing this? Automaton, thank you. The function g increases on the intervals negative infinity to 0 and 2 to infinity. Do you see that in our picture? Because g prime is 0 for all x in these intervals. So this is you writing, period. Full sentences with capital at the beginning, period at the end. The function g decreases on 0 to 2 because g prime is less than 0. So you see, another important thing I want to make note of is the fact that you didn't say this. This is very dangerous. This is like the most dangerous part of the course, to use the word it. Do never say it decreases or it increases. Well, hold up. We have like 3 functions we're now talking about. So make sure you're really clear. G is increasing. Why? Well, because g prime is positive. Don't say it's increasing because it's positive. Like, no one knows what you're talking about, right? So make sure you're really clear about not using pronouns, okay? So this is, I know this seems wordy, but like this is the kind of explanations that are expected when they ask you to justify or explain your answer on these kinds of things. Is that, are we done, I guess? All right. Come on, guys. Let's do a couple more. You'll be fine for homework 3 from the book tonight, all right? So thanks for hanging with me here.
Am I your mate? What?
Yes, I know. This is the first thing this year, even